Okay, so in the last video, we figured out how to build symmetry-adapted linear combinations of atomic orbitals. And this time, we're going to actually use them to build molecular orbital diagrams. So we start with what we talked about in the last step. So steps previously, which I'll call step 0 here. Find your salks. And then also your central atoms from the atomic orbitals. OK. And then for your molecular orbital diagrams, what we first want to do is start with atomic orbital energies. If you have the Meissner-Tar textbook, there's a table in chapter 5 where they list you atomic orbital energies for like the 2s2p orbitals for different elements, et cetera, depending on which row it's in. So that's how we know like where along our energy axis our atomic orbitals lie. And then once we have those, then we can interact them to form our new stabilized and destabilized molecular orbitals. OK, so once we have that, and then finally, so then you want to interact to form stabilized and or destabilized, I'll put this in parentheses, molecular orbitals. Again, if you form a bonding orbital, it's stabilized in energy, and then that's usually represented by in-phase interactions of your orbitals. If you have out-of-phase interactions, then they're destabilized and anti-bonding. So that's something to keep in mind. And then lastly, you want to fill in with electrons. Fill in with the number of electrons that you know. Okay, key things to keep in mind, of course, is that number of electrons is the same as the number from your free atoms. And then also another thing to keep in mind is number of atomic orbitals in equals number of molecular orbitals out. So this is critical, and we'll talk about the nuances of this a little bit later. But hopefully this makes sense because we have a certain number of things of one symmetry, they interact, and then the linear combinations you can only form the same number out. OK, so let's do a quick example. Let's do first example, no central atom. Example 1, no central atom. So let's consider this molecule, H3+. And we'll consider the triangular potential isomer. OK, so from our previous video, we need to find our symmetry-adapted linear combinations. Step 1, we're going to find the point group. So this is D3H. And the basis set is going to be the 3 1s orbitals of these 3 hydrogen atoms. Those are their valence orbitals. Then we need to find our reducible representation. So let's do that. D3H, it's going to be E, 2 C3s, 3 C2 primes, sigma H, S3, and then 3 sigma Vs. OK, that's somewhat cut off, but I'll try to remember to move it over a little bit. OK, so again, as we go through, this is the thing where we have our matrices and off-diagonal elements if it moves. So E, there's 3 1s orbitals. If we do C3, they all move. It's a 0. C2 prime, right? C2 prime is going through one of the hydrogens. So one of them doesn't move for each of them. And then sigma H, they all stay the same. If we do an S3, they all move. If we do a sigma V, it's the mirror plane containing that C2 axis, so one of them stays the same. And then if we then reduce this down, this gives us, we have A1 prime plus E prime. And if we project this sulk, we know that our A1 prime sulk is where they're all in phase. Phi1 equals phi2, or phi1 plus phi2 plus phi3. And then our E prime sulk is going to just be the one that looks sort of like there's twice as big as the other 2, and the other 2 are out of phase. And then we have one where there's a middle node, and then we have this guy. So these are our 2 E primes. So those are our salks. And so now we need to figure out how to then interact these to form a molecular orbital diagram. Okay, so since we have no central atom, we can actually just see how each of these atomic orbitals are interacting and then see whether they're stabilized or destabilized. So you see here, this is the A1 prime. It's got to be stabilized because they're all in phase. They're all symmetric. So we have a net stabilizing due to the overlap of these atomic orbital wave functions. In this E prime, what you see here is the E prime has to be two orbitals, but they have to be degenerate because E prime is doubly degenerate. So they're the same energy. And what we see is that this is an anti-bonding interaction. They're out of phase. So overall, this has got to be destabilized from the energy of the hydrogen atomic orbital. So what this looks like is so first we start off with our atomic orbital energies. So this is our y-axis is energy. So we'll start off with our 3 hydrogen atoms. So I'm drawing these 3 lines together. They're all the same energy because they're all hydrogen atoms. Hydrogen atoms must have the same energy because they're all hydrogen. So here are our 3 hydrogen atoms. And of course, these are the 1s orbitals. And then, so keep in mind, so they're all degenerate because they're all far apart. So they're all acting like uninteracting hydrogen atoms. And then keep in mind, of course, this is A1 prime plus E. So now we can form a bonding combination. So this is going to be stabilized. Note that I'm not really saying kind of the magnitude. We can talk a little bit more about what goes into that in the next couple classes. So this is one stabilized orbital, A1 prime, and we draw it. And then we have our anti-bonding destabilized orbital, E prime, which again is 2 orbitals. So there's 2 lines here because these are 2 molecular orbitals that are the same energy. And then we would have to draw both, and those are the salks that we just found. And I'll just put a dot here. Yeah, and then after that, we fill in with electrons. So 3 hydrogen atoms. So the neutral H3 molecule should have 3 electrons because every hydrogen atom has 1 electron, but we overall have a cation. So we actually only have 2 electrons starting here, unpaired. And then we fill them in at the end. And then you can see here, this would be our final molecular orbital diagram. We have 2 electrons in this bonding type orbital, and then 0 electrons in this anti-bonding orbital. But keep in mind, these are orbitals with different symmetries. And then so overall, the conclusion is you can see that H3 plus is stable. Okay, I won't say it's not obviously not what you see in nature. So stable has kind of a different connotation. What I mean here is that because of this stabilized bonding interaction, this is stabilized from 3 separate H atoms. So it's not more stable than H2, but you can see it's stabilized overall. And in comparison, if we started then filling in to our neutral H3 molecule, if we add another electron, we reduce this cation, you can see we're populating this anti-bonding orbital higher in energy. So overall, the neutral H3 molecule is higher in energy. Molecules want to go down in energy to be more stable. So H3 plus is more stable than the neutral H3 triangle because the neutral H3 triangle has this electron in the anti-bonding orbital. We have lower bond order, weaker bonding. And then so it might tend to fall apart more readily. So that's why molecular orbitals are useful. We can start interpreting what they mean for reactivity and other electronic properties of the molecules we're studying.